I want to look at different types of mechanisms. So radical mechanisms, I want to give you an example that's going to involve our homolytic and homogenic breaking and making radical intermediates. Again, we're not going to see a lot of examples of that this semester beyond the one I'm about to give you, but you will do a few of them in 236. And then polar mechanisms, which is what most organic mechanisms are. It's what we're going to be doing in this semester. And then some pericyclic ones, which are kind of cool, but again, you won't really get a lot of examples of those until 236. So common, one being far more common than the other. Let's just say types of mechanisms. So our first one, radical. So these involve our symmetrical bond breaking and forming. So homolytic and homogenic. Bond breaking and forming. Right, our symmetrical ones, we could put that underneath it. It's going to involve radical intermediates. So I'm going to go through an example with an alkane. Alkanes are actually, from a chemical standpoint, one of our less reactive functional groups. So alkanes can undergo combustion reactions. You would have learned those probably back in your 130 days. So I take some sort of fuel, I react it with oxygen, we get carbon dioxide and water. So that would be a combustion reaction. So alkanes can undergo those, and then they can undergo these radical reactions that I'm going to show you. So these would be halogenations. So I'm going to start with propane. Actually, let's start at the beginning. I'm going to kind of do it the way that I would write it. So I'm going to have propane. Let's do chlorine. I'm going to show a solvent. We need ultraviolet light. And then I'm going to substitute these two hydrogens with a chlorine. So it is a substitution reaction. I had on that middle carbon 2 hydrogens. In my products, I have a chlorine and 1 hydrogen. And then my right carbon on my reactant side, I had 3 hydrogen. On the product side, I have 2 hydrogen and a chlorine. So it is a substitution reaction. The mechanism is going to be a radical mechanism. So most radical mechanisms have 3 parts to them. The first part is going to be initiation. And in initiation, we need to make a radical. It's not going to react unless we have a radical to initiate it, and that's what our ultraviolet light is, or our light energy is going to be. So what I'm going to do is I'm going to take my 2 chlorines, we're going to add our light energy to it, and I'm going to do a homolytic bond breakage. So I'm going to put 1 electron on chlorine, 1 electron on the other chlorine. Again, both of those arrows could go up or they could go down, but I'm going to end up with 2 chlorine radicals. Now that I have a radical, it's just going to kind of go and do its thing. It's going to start taking electrons. So my second step is called propagation. And I don't care if you remember the names of these. I just want, if I give you a radical mechanism, be able to recognize it as such. If I tell you that it's a radical mechanism and I give you, let's say what I just did here, if I give you the products and the reactants, be able to add those arrows. If I give you just the reactants with the arrows, be able to write the product. I'm not going to say what's the first step of a radical mechanism called. Like, I won't ask that. So propagation, though I am writing it down. So what I'm going to do now is I'm going to take my propane molecule, and I do need to draw out one of those hydrogen. If I'm going to substitute, I have to show that bond, right? I need those electrons, right? That line is representing those electrons so we can break it, right? Remember, in a mechanism, every bond that gets formed and broken, I have to show. So I'm going to have to draw one of those hydrogens out. And then I have my chlorine radical hanging out here. So what's going to happen is that chlorine radical is going to take one of those electrons that's between the hydrogen and the carbon. So one of these is going to meet this one somewhere out in the middle. And then remember, that line is 2 electrons. That other electron is going to go on to that carbon. And again, I need to draw those fishhook arrows. So what I have now is I have carbon with a lone electron, right? One of those 2 electrons between carbon and hydrogen went onto that carbon. And then I have a bond between HCl, right? The 1 electron from chlorine formed a connection with the other electron from hydrogen. So this is what we got now. I have another chlorine. So I'm going to throw another chlorine in, not a radical, but just a straight up chlorine. And I'm going to move it on the top because it'll be easier to get my arrows right, or to make them look not so weird. Remember, we never just have one molecule, right? If I had 1 mole, which isn't a whole lot, if I had 1 mole, I have 6.022 times 10 to the 23rd of these. My chlorine is probably not going to be my limiting reactant, so you can have more than one of them. I write 1 on the arrow, but we know we don't have 1 little molecule of chlorine, right? If we're in lab doing this, we don't have a single molecule. So I got another one. What's going to happen now is one of those electrons, fishhook arrows are kind of awkward to draw. So one of those is going to combine with that, and then this other one is going to go onto chlorine. And again, whether you draw them up or down, it doesn't matter. Just make sure that they have the 1 barb on it. That one's kind of messy. So I now have done my first substitution. I now have a chlorine bonded to this, and I have another chlorine radical floating around. I did have a radical intermediate. And then essentially we're just going to repeat that 1 more time. The reason I'm saying 1 more time is because I already gave it a product that had 2 of them on it, so that's what I'm trying to make. So I need to draw another hydrogen out. And then again, like, we're literally just repeating that. So I have a chlorine radical. One of these electrons from hydrogen is going to combine with this. This other one goes on to carbon. I now have another radical intermediate. I have another chlorine floating around. One of those electrons is going to combine with one of those electrons. It's a really big arrow. The other one's going on to chlorine. And I now have 2 substitutions. I do have, after this step here, I do have another HCl. As I warned you, I don't always write all of the products, right? I'm not always balancing everything, but there is another HCl floating around too. So as you would imagine, there's more hydrogen, right? There's 2 more hydrogen on here, there's another hydrogen here, there's 3 more here. I do have a radical that I produced after that step. So as long as you have a radical, it's going to keep reacting until all of those hydrogens are substituted. Or step 3, we terminate the reaction. So in order to terminate the reaction, I have to have 2 radicals collide. If 2 radicals react, then I don't have a radical anymore and it'll stop. So as long as I have a radical, we're going to keep with propagation. If 2 radicals react, I don't have a radical anymore and my reaction is going to stop. So for this one, we could just say 2 radicals combine or react, form a bond, however you want to say it. So if I'm not forming radicals, I'm going to stop. It's going to terminate the reaction. So an example of a radical mechanism. Again, you're not going to be completely responsible for this reaction or this mechanism until 236, but I do want you to know something about it. I want you to know that radical mechanisms involve the symmetrical bond breaking and forming, right? Homolytic, homogenic, and know that it involves radical intermediates. And then if I drive parts of this, be able to supply the rest. So if I give you reactants and an intermediate, supply arrows. If I give you reactants plus arrows, be able to draw the intermediate or the product. If I draw it all, be able to identify the intermediate, right? We have 2 intermediates here, actually 3, right? This is an intermediate, as is this one, because we're making it and then using up, and then making it and using it up. So just be essentially familiar with it. Polar mechanisms, these are the ones that we're going to see pretty much exclusively this semester. And even inorganic too. So in 236, most of the mechanisms you're going to see are polar. They're by far the more common one. So these are the most common type. So these are the ones that involve the heterolytic and heterogenic bond breaking and forming. They're going to involve our carbocation and carbanion intermediates. So heterolytic and heterogenic. Bond breaking and forming. Involves carbocation and carbanion intermediates. It involves nucleophiles and electrophiles. Right? Remember, my nucleophile is my electron source. My electrophile is my electron receptor, right? Nucleophiles are electron rich, electrophiles are electron poor. And then remember that our arrows, right, always go from the nucleophile to my electrophile. And we're doing the 2 barbs, right, because I'm moving 2 electrons. We've already seen an example with this one, the first one that I did. Let's do another. This one, we'll just do a short substitution. So let's just have chlorine leave. Oops. So it's taking both of those electrons with it. So I'm going to end up with a carbocation intermediate. And then I should have probably wrote out the reaction for you first, but I'm going to have SH minus. And it's going to add to that carbon. Again, 2 barbs because it actually has a couple lone pairs on it, 3 of them. But it's 2 electrons, right? My bond is 2 electrons, and that carbocation doesn't have any electrons to contribute, so both of them are coming from that sulfur. So I have a carbocation intermediate. We've seen lots of examples of these, so I didn't write the reaction first, I just jumped into the mechanism, but if I was to write the reaction for something like this, and I'd probably give you a cation with it, you just can't have anion, so I'd probably give you something like NaSH, And we know that sodium is a spectator ion. We know that it's Na+, and I'm not going to really care about it. And I have SH- as my nucleophile. And then my product was my substituted product. And then I also have sodium chloride, dissociated, of course, and hanging out. I often wouldn't show those. I would just show the first part that I drew. But I do have sodium chloride also. You can show them. I'm not saying you don't have to. I just don't tend to focus on the rest of the reagents, which I know is frustrating for students when they're learning, because it's like, well, what happened to sodium? It's there. I just didn't draw it. Right? What happened to chlorine? It's there. I just didn't draw it. And I'm okay with you guys, as long as you get this part. If you leave that part off, I'm okay with it. So back up to the mechanism itself, right? I'm breaking the bond between carbon and chlorine, and I'm doing it unsymmetrically, right? Both of those electrons are going onto chlorine, right? I have chlorine floating around here. It had 3 lone pairs, and now it has 4 and then negative charge. And then I'm forming a bond between the carbocation intermediate and that sulfur, and both of those electrons, again, unsymmetrical, both those electrons are coming from sulfur, right? They're not each contributing one like they would in a radical mechanism. One more for us, and that's pericyclic. And this is another one that you won't really be responsible for, doing on your own until 236, though I do want you to know that it exists. And then if I give you one, be able to identify it. If I supply arrows, be able to give me the product. If I give you the reactant and the product, be able to supply the arrows. And what this one is it's a concerted movement of electrons. So this is going to happen in one step. So we are going to draw the transition state for it. And that transition state is going to be cyclic. So peri means around. So basically I'm going to go around in a circle. Right? That's what pericyclic means. So it's going to be a concerted movement of electrons. And we're going to have a cyclic transition state. So my example, we'll write it as a reaction first. Do this one. And actually, let's just do regular 2 carbons. Let's do ethene. 2 carbons is S, right? And then alkenes end in ene, so that's ethene. And then we do need some heat. And what I'm going to end up with is this. So that would be my reaction. And then we'll do our mechanism. So what I'm going to do is I'm going to take my reactant, which is this part, and I'm going to draw it sideways, and then I'm going to draw it in a different conformation. It's actually called the S-Cis Conformation. So what that means is my 2 double bonds are on the same side of my single bond. So the S for single bond, and then cis, because those 2 double bonds are on the same side of that single bond. So I'm going to draw it in my S-Cis conformation. I'm going to take my ethene and I'm going to draw it 90 degrees from how I have it in my reaction. So I'm set up now. You can kind of see how I'm going to get that ring. So what's going to happen, this happens all at the same time, is pi electrons are going to grab onto that carbon. That carbon's going to have too many bonds. So those electrons are going to go up. That's going to give this carbon right here too many electrons. So then those electrons are going to go grab onto that carbon. So concerted movement of electrons. I am going to draw the transition state. And remember, with a transition state, I'm drawing a dotted line for everything that I'm forming and breaking. So just kind of drawing part of it here. I'm breaking this pi bond, so that's going to be dotted. I'm forming a bond between this carbon right here and this carbon right here. So I'm going to draw a dotted line between them. I'm breaking this pi bond right here. So that's going to be a dotted line. Those electrons get moved to where that single bond is, so that's going to be a dotted line. I break that upper pi bond, so that's going to be a dotted line. And then those electrons are grabbing onto the top carbon of what used to be ethene, so that's a dotted line. So I have a cyclic transition state. With the transition states, we'll put brackets around it in a double dagger, and then I can just draw my product. So again, we're not going to really see, besides now and, some questions that I could ask on an exam about it, you won't be responsible for the complete mechanism until next semester.